Welcome to Module 2. Our first topic for Module 2 is about partial differentiation. At the end of this lesson, you must be able to find the derivative of a function in two or more independent variables using partial differentiation. So let us first define what partial derivatives of a function are. Let us consider having a function z, the f function of xy. Here we have two independent variables, x and y. Then the partial derivative of f with respect to one of its independent variable x, also called the partial derivative of z with respect to x, is the derivative of the function with respect to x done while holding y as a constant. This partial derivative is denoted by the symbol f of xy sub x, read as partial derivative of xy with respect to x, and is given by the partial derivative of xy with respect to x, also denoted by the symbol read as partial derivative of f of xy with respect to x, is simply the limit of the ratio of the difference of the functions f of x plus delta x y minus f of xy divided by delta x as delta x approaches 0. Now please take note that in this definition of the function, y is held constant, that it is only x that would vary in value. Similarly, the partial derivative of f with respect to y, also called the partial derivative of z with respect to y, is the derivative of the function with respect to y done while holding x as a constant. This partial derivative is denoted by the symbol partial derivative of xy with respect to y, and is given by the partial derivative of xy with respect to y, also denoted by the symbol, giving us partial derivative of f of xy with respect to y, will be the limit of the difference in the functions f of x, y plus delta y, minus f of x, y, divided by delta y as delta y approaches 0. Let us now look at different notations for partial derivatives. Consider z a function dependent in two variables x and y, where x is the first of the independent variable and y the second. The first partial derivative of z with respect to x would be denoted by any of the following symbols. You have partial derivative of z with respect to x, or you can have the subscript notation z sub x or z sub 1, indicating a subscript the variable of differentiation, or we can have partial derivative of f with respect to x, or f sub x, f sub 1. So the first partial derivative of z with respect to y is now denoted by any of the following. We have partial derivative of z with respect to y, or we have z sub y, z sub 2, or partial derivative of f with respect to y, or we have f sub y or f sub 2. Higher order partial derivatives of some function can also be defined. So the second partial derivative of z twice with respect to x is defined as the partial derivative with respect to x of the first partial derivative of z with respect to x, and is denoted by this symbol. This is read as second partial derivative of z twice with respect to x. And in terms of the other notations, we have z sub xx, or z sub 1, 1, or second partial derivative of f twice with respect to x, or an f sub xx or f sub 1, 1. A second partial derivative of z can be defined first with respect to x then with respect to y. When the variable of differentiation are different from one another, what we have is a second mixed partial. And this is defined in terms of the partial derivative with respect to y of the first partial derivative of z with respect to x, denoted by the symbol second partial derivative of z, first with respect to x, then with respect to y. The other symbols that would represent these are z sub xy or z sub 1, 1, or second partial derivative of f, first with respect to x, then with respect to y, or we have f sub xy or f sub 1, 2. Now, please take note of the order of differentiation. If the symbol used is like this, the order of differentiation is from right moving out to left. So you do first partial derivative with respect to x, followed by a partial derivative with respect to y. But if you are using the subscript notation, then the order of differentiation will be from left moving out to right, doing first partial derivative with respect to x, followed by partial derivative with respect to y. Let us now work with some examples. That given the function f of xy equal to 2x to the fourth times y cubed, let us find the following. For letter A, the first partial derivative of the function f of xy with respect to x. Remember that when you are doing first partial derivative of a function with respect to x, you just differentiate it with respect to x, holding the other variable as a constant. So here, the partial derivative of the function f of xy with respect to x is simply the product of 2y cubed, which is held constant, times the derivative of x to the fourth given by 4x cubed, or we have 8x cubed y cubed. For the first partial derivative of the function f of xy with respect to y, we will now be differentiating the said function with respect to y while holding the x component constant. So this will give us the first partial derivative of the function f of xy with respect to y equal to the product of the factor 2x to the fourth, which is considered constant, times the derivative of y cubed, which is given by 3y squared. So what we have here is 6 times x to the fourth times y squared. As to evaluating the first partial derivative of the function with respect to x at x equal to 2 and y equal to 1, then this will just be given by the value of the function defining the first partial derivative of f with respect to x, substituting in place of x 2, and retaining y value as y. Hence, in this expression here or in there, we just substitute 2 in place of x to give us this expression here, or simply we have 64y cubed. For our second example, let us have the function z defined equal to 3 times e to the x cubed y squared. And for this given function z, let us determine the partial derivative of z with respect to x and its partial derivative with respect to y. So working on the partial derivative of z with respect to x, we will just be differentiating this function, which we recognize is an exponential function. So the derivative would be equal to the factor 3 times e to the x cubed y squared times the derivative of the exponent. But this we will be differentiating partially with respect to x, and therefore we will be considering y constant. And the partial derivative of z with respect to x would now be given by 3 e to the x cubed y squared times the partial derivative of x cubed y squared with respect to x, which is given by y squared times 3x squared, such that the partial derivative of z with respect to x is now given by 9x squared y squared times e to the x cubed y squared. As to the partial derivative of z with respect to y, we differentiate again this said function, but now we will be holding x constant. And again, applying the rule to differentiate an exponential function of the form e to the u, whose derivative is e to the u du dx, then the partial derivative of z with respect to y is given by 3 times e to the x cubed y squared times the partial derivative of x cubed y squared with respect to y, giving us now partial derivative of z with respect to y equal to 6 x cubed y times e to the x cubed y squared. As we can see in this lesson, if we are given a function that is dependent in two or more variables, then we can differentiate this function partially with respect to one of its independent variables, doing it while holding the other variables constant.